Okay, we're going to talk about PIN photodiodes. PIN stands for positive intrinsic negative diode, and we're going to learn that that's different regions of the electrical component, different parts of it. Now, you can call it a diode or photodiode. Photodiode is a use. It is still a diode. All right, the topics we're going to cover is the overall placement of a PIN photodiode in our telecommunication systems. We're going to first talk about key N, positive negative diodes. And we're going to talk on those in three cases, under positive voltage, under negative voltage, and under zero voltage. We're going to then talk about the PIN diode under zero voltage, which is called the photovoltaic mode. It's going to produce electricity under positive voltage and under negative voltage or reverse voltage. And that's the photoconductive, and that's what we use in telecom. Then we're going to look at just as the PIN is an improvement upon the PN diode, the avalanche photodiode is an improvement upon the PIN. Then we're going to compare the different diodes. All right, PIN diode is able to convert an optical signal into an electric signal. From end to end in our telecommunication system, we start with an electrical signal, then a laser, an amplifier, and modulator all working together convert the electric signal into an optical signal. The optical signal is transmitted along lengths of fiber, perhaps using transceivers or amplifiers. Then the light is shined upon a photosensor, a photodiode, such as a pin, to convert the optical signal back to an electrical signal. Here we take a look at just a regular PN diode under zero voltage. We'll notice that it's comprised of basically two regions, a negative region and a positive region. This region of negative is doped with electron donors, and this P region is doped with electron receivers. The yellow area is what's called the depletion zone, and it is around where the P and N meet. What basically happens is some of the positives combine with some of the negatives and cancel each other out. So in the PN junction, we have no what are called free charge carriers, nothing to carry a current. So the depletion zone acts as an insulator between the positive and negative. So no current will flow. Under a positive voltage, we have a enough the depletion zone sinks or retreats or gets smaller, whatever word you prefer to use. The energy to go over the depletion zone is less. So if we put a positive voltage on the depletion zone, we're going to be able to get some current. This is the signal electrical diagram for a diode, which will not let any current pass under low voltage, but under higher voltage, it will act just like a piece of wire. It'll let current pass unimpeded. Okay, what I would like you to note is that for the diode, the charge carriers are coming from the P and N regions themselves. Okay, here we have the PN diode under a reverse voltage, under a negative voltage. And what that's going to do is that is going to widen the depletion layer. Now, almost no current flows. A little bit of current will flow, and that's called a dark current. And that's some of the negative has enough energy to make it across to the positive. But that is very little. What happens under a negative voltage is a photon, a piece of light, can come and hit in the N or the P region and make a ion and a free electron. The ion is going to migrate, the hole it's called, is going to migrate to the negative part, the N region, and the electron is going to migrate to the P region, and that is going to cause a current. So we have a current due to a piece of light ionizing an atom. Now, note that this means that my PN diode can be used as a photodiode. And the most important thing to notice about the PN diode is that the current originates from the P and N materials themselves. It takes a long time for charge to diffuse, it's called, go across this depletion layer. So the response time of PN photodiodes is relatively slow. So we can improve that by making a PIN diode. And what we do is we still have our P dope region, our N dope region, but we have an intrinsic region, which is a semiconductor that's not doped. There's no charge carriers here. All right. The intrinsic zone is going to act as an insulator. It effectively increases the size of the depletion zone. All right, under positive voltage, the pin just works as a variable resistor instrument. If you're not used to electric circuits, that really doesn't mean much. Resistors are a basic component of electrical circuits, and sometimes it's necessary to use a resistor where we can vary the resistance. Under zero voltage, interesting enough, it's a photovoltaic cell. It will actually generate power from light. But of most interest to us is the PIN diode under negative voltage. Okay, under negative voltage, light is going to hit, but light's going to hit in the intrinsic region. And the intrinsic region is going to create ion electron pairs, holes and electrons. But the holes and electrons are created in the intrinsic region already, so they don't have to transverse as much as the intrinsic region. That's why PIN photodiodes response time is much quicker. They don't have to do that migration across the intrinsic zone that you had to do with a photodiode. All right, PIN diodes has a high speed, just as I mentioned, because the charge carriers are made in the intrinsic region. They're highly linear, which says that the amount of current generated is proportional to the amount of light, something you want if you're measuring something. And they have low noise, low dark current. Here it shows you an example of a PIN diode and under a reverse bias. So what's going to happen is the negative part of the battery is going to attract all of the positive charges. So these aren't going to be used in the current. The positive part's going to attract the free electrons. To compensate for the holes and electrons, a charge builds up in the intrinsic zone. And when light hits the intrinsic zone and creates a hole electron pair, what will happen is the holes will migrate towards this built up negative charge and the electrons will go towards this built up positive charge. So the overall summary is that the photoelectric effect, the ionization of atoms by light, is happening in the intrinsic zone. And because it's happening in the intrinsic zone, detection of the current is much faster response time. Okay. Now we have different photodiodes. We have some made of silicon, which are good for ultraviolet light and for visible light. We have germanium. We have indium gallium arsenide. Both these are used for telecommunication equipment. And again, at visible light, what we have is gallium arsenide. All right. From a pin diode, an avalanche diode is a small step, a very important step. The advanced photodiode is built by simply adding a p-doped layer in a conventional pin diode. I have a picture here where it shows the additional p layer in red over here. The avalanche photodiode operates at a high voltage from about 100 volts to about 1.5 kilovolts, as opposed to under 1 volt with the pin diode. The high voltage gives the ions and electrons a lot of energy. It accelerates them. When it accelerates them, it gives them enough energy. The ions are created by, again, some light. The ions are going to strike neutral atoms, and those neutral atoms are then going to become ionized, making more ions. More ions here. Those ions in turn strike other neutral atoms, which in turn strike others, which in turn strike others. So our one charge carrier here gets multiplied into many charge carriers. And this could happen more than 3 generations. It depends on the intrinsic material and what's called its band gap energy compared to the energy of the light. Okay. The avalanche photodiode can operate with less light because of this avalanche effect. So at the end of a long cable run, there's less light. So the avalanche diode is better. The avalanche diode is much faster than a PN or PIN photodiode. Yeah, again, the picture of an avalanche photodiode and the chain reaction that occurs to create more charge carriers, making it faster and able to operate in lower light. All right, here we have some timings of the response times of different types of diodes. A standard PN is going to be down around microseconds, so I can get megabytes out of it. A pin diode can operate in nanoseconds, so I can get gigahertz out of it. The avalanche photodiode, well, that's sub-nanoseconds. So here I can get the 40, 100 gigahertz speeds with the avalanche photodiode. It might seem like, well, the way to go is the avalanche photodiode. And that's true if you're in a low light condition or you want the highest possible bit rate. The problem is because of the high voltage, it creates a higher degree of noise. So some electronics have to be added to separate the signal from the noise. It is the most expensive. It does not make a good solar panel. Tin, on the other hand, is best if you want a low noise detector, but it's not as fast as the ADP. Finally, if you want low cost or you want a solar energy, want a solar energy device, the best is going to be the PN photodiode. All right. So for the PN diode, photodiode, the PIN photodiode, and the avalanche photodiode, we have examined their physical structures, discussed their operating principles, shown the operational wavelengths for each material type that we make the PIN or avalanche photodiode or the PN diode on, and compared key parameters of these three, including bandwidth. Thank you.